Hello. Today's lesson is about relating what we know about a graph of a function and its derivative. In other words, the graph of a function and the graph of its slope. So this is simply today about polynomials, so not getting into too much detail. So when we're talking about the graph of f prime, or the graph of the derivative, or even the function itself, we've seen before that we know that will be 1 degree less than the graph of the original function, but again, that's only when we're dealing with polynomials. When we talk about a critical point on f, all sorts of things can happen at a critical point. There might not be a graph. I could have an undefined slope there, but typically the things that help us are locating maximum and minimum values. So on a polynomial, we don't have NPVs, we don't have vertical asymptotes. So if we're talking polynomials and I found a critical point, there's a really good chance it's a max or a min. Now, the max or a min on a graph, therefore, if it is a max or a min, we know the slope there is 0. How does that show up on the graph of a derivative? That will end up being that graph's x-intercepts. So we really need, sometimes when we draw derivative graphs, it gets our head spinning. We don't necessarily see the one-to-one connection until we stop and think about this for a minute. There is my original graph. This is going to be my slope graph. So everything that I see, so I've just drawn a duplicate line underneath, everything I see on this graph is telling me which way this is heading, not where it is. If I just want to know where this graph is, most of it is above the x-axis. So most of f is positive from what I can see. But it is not constantly doing the same thing. It is increasing, leveling out, decreasing, leveling out, increasing. That's the stuff I'm going to see on a slope graph. It's talking about this guy's direction. So basic points where you should always want to start from would be from real obvious spots on this graph, which would be this where slopes are 0. So a spot right here, my slope is 0. A spot like right here, my slope is 0, and over here again, my slope is 0. So if that is where I would start, I would take a ruler, give myself some nice long dotted lines connecting to the graph below, and put a dot there. From my other situation where slope was 0, I would do the same, and I would do the same there. So now I have, for sure, 3 points that are going to be on the derivative graph. Now what else? This is talking about f's direction. This is heading up. To show that I'm heading up means that the slope is positive. Then I go to heading downward, so my slope is negative. Heading up, my slope is positive. Here my slope was 0. Heading down, my slope is negative. Negative and decreasing don't necessarily have the same meaning. You have to watch your wording. So to show a positive slope on a slope graph, I need to be above the x-axis. So in this positive region, or in this positive slope, I need to be here in a positive region. So I'm going to give myself a little bubble. For now, that's it. I know that's where I'm going to be drawing in a minute. From here to here, I have a negative slope. Negative slopes on a slope graph get drawn here. From here to here, positive. So I need to be drawing somewhere here. After point C, my slope is forever negative. So the idea is I pretty much get I have to be following through these regions, but you need more precision. POIs come into play. When you go from concave down to concave up, you are talking about a change in slope. Now you have to watch your wording. Right here, this is a POI. Up to this point, I'm definitely concave down. So from there to there, for sure, I'm concave down. And then something happens. I now go, and now I'm concave up. I'm not going to say right here, oh, I went from a positive or negative to a positive slope. No, I didn't. As I came through this change in concavity, my slope remained negative, but there was something else I can say. So if you have a look at this, okay? So when we talk about concavity, in a concave down interval, your slopes of the tangent lines are not always negative. Right here, the slope would be positive, maybe 4. Now the slope of the tangent line is 1/2. Then it moves to -5. So the slopes weren't negative, but they did, as I continue to the right, get smaller and smaller. So in a concave down interval, your slope decreases. Don't say it's negative. In a concave up region, maybe right here, my slope is -4, then it went to -1/2. Over here, it's 3. My slope was increasing. Don't say it was positive, but it was increasing. So that's going to be very important when I look at what was happening here. I went from a concave down or decreasing slope to a concave up or an increasing slope. So on a slope graph, how do you show decreasing to increasing? That would be a max or a min. Decreasing to increasing would be a min. So you actually need the information from these POIs as well. So you could take your ruler, give yourself some more guidelines with some dotted lines down from that POI. Do the same thing here, some dotted lines. Now you have a lot of good guidelines when it's time to stop increasing and go to decreasing. Okay, so in a positive region, I need to be over here, so maybe I'm going to start about here. I know this graph is heading down, but it is in a positive region on a slope graph. A positive region of a slope on a slope graph means the slope of where it came from was positive. And it is. From here to here, this is a positive slope. So that is what is being portrayed here. Then it became decreasing all the way to B. So I need to be drawing down here all the way there. But what did happen, at this point, from concave down to concave up, I went from decreasing slope to increasing slope. So that right here is my time to stop decreasing and start increasing. So I've made it through that region. So now I'm increasing all the way to there. But at this point, I stopped having an increasing slope and went to a decreasing slope. So I'm going to go here from an increasing slope, and now I would have to change what I'm doing to a decreasing slope. And after that, there's kind of no choice. So this is 3rd degree, this is 4th degree, if you want to look at it that way, because they're polynomials. But interpreting this and looking at this, you need to spend some time and do that. Realize, what is this telling you about this graph? Don't say, oh, well, this headed down forever from here, so this guy must be heading down. That's not what this is saying. This is telling you about the direction of of the one it came from. So as a summary, what can we say? If the slope of the original graph is positive, then the value on the derivative graph will also be positive. So you will be drawing above the x-axis. If the slope of the original graph was negative, then the y value, right, on the derivative graph will also be negative. In other words, you will be drawing negative slopes below the x-axis. And where this had points of inflection, we can all of a sudden look here and see they became the maxes and mins on the derivative graph. That's where you changed from increasing to decreasing. So points of inflection on the original graph become the max, the maximum, and minimum points on the derivative graph. Okay, we could have drawn one more after this. Actually, we could have put one more line and started from here. Where do these have 0 slopes? There'd be your starting point, and go from there. But we're going to do one more. So I have this graph here. Okay, so again, a polynomial graph. Where do I want to start? Where its slopes for sure are 0. So I'm pretty confident there and there are slopes of 0. I'm not very confident right here that's a slope of 0. I think it's probably positive, but I wouldn't say it's 0. You take your ruler, give yourself your dotted lines, draw long dotted lines all the way through. They, on the derivative graph, become the x-intercepts. Now what? This graph headed down. So left of this dot, this graph is a negative slope. I'm going to be drawing here. Between these 2 points, the graph here forever was increasing. I mean, it wasn't 0. So forever increasing. So positive slope from here to here. So on my derivative graph, that's where I'm drawing. Maybe with some ups and downs, but that's where I'm drawing. And then negative slope after is here. I need to look at the POIs. If I'm checking out this graph and kind of moving along, I'm pretty comfortable this thing is concave up until about here. I start getting this feeling it's not concave up anymore. It lost that maybe about right there. So right here, I think is a really important spot. That's a POI. That's where I changed from on this side being confident it was concave up to now on this side looking at it and saying, I know it's tiny to see, I'm concave down now. But the more I start moving over, I lose that concave down look and it starts becoming concave up. Maybe about right here. So here I have another POI. So after I leave here, pretty sure I'm concave up until a little bit down the road where I get that feeling it's changing again. Where did it stop being concave up? I don't know, maybe about right here. So now I stop being concave up and now I'm concave down. When is it going to stop being concave down? It's not. So those points come into play. So from each of those, you could draw yourself some guidelines or some dotted lines. They'll tell you where these guys, where F prime has its maxes and its mins. So let's do this. I am decreasing. Then I hit a slope of 0. So I must be here somewhere. I should probably use a pencil because I might change my mind about what I'm doing here. So decreasing, so I'm drawing here. So it increases forever, but the concavity changes. This was an increasing slope because it's concave up. Then it's going to change to a decreasing slope. Think about it. How will you show decreasing on this one? It needs to head down. So this POI is kind of your heads up, okay, whoop, time to stop increasing, I'm going to decrease. Now, how far are you going to decrease to? Should I take this all the way to here? If I came to this point, it tells me this has a 0 slope. It has a max or a min. So I can't go that far down. So I came kind of to a max, maybe to here. This slope is a positive value. It's very small. So the y value here would be positive and small as well. Then I'm concave up. So I'm increasing. So this could now turn this way, right? So now I'm doing increasing. And I'm increasing and increasing. And then there's going to come a time where I have to turn around and be decreasing. So all of a sudden, it kind of takes me through. That's why you're going to want to use a pencil when you're done here. Nothing should be sharp. These aren't pyramids. These aren't points. This is you changing from concave up to concave down. So when you're done with this kind of stuff, this pretty much is what you will end up with. This was an odd degree, and I can see this is an even degree, so I probably have lost 1 degree value. So again, have a look at this, replay it, think about the thinking, why you stopped moving in one direction into another, why we didn't go down to here. So this handout, there's a blank copy attached for you on your classwork section. The second page of this, there are really just 6 graphs. There are 3 up here because these are the answers. And there are 3 graphs here, and then these are the answers. So what do we mean by answers are the derivative graphs. But they're there so that you could draw them in practice. So for example, if I wanted, let's say, to try this one, I should duplicate this y-axis right underneath for me and an x-axis. So what would be my starting point here? Always where slopes are 0. So right there. That's the slope of 0. So I'm holding this blank piece of paper underneath, and I'm going to take my ruler and I'm going to give myself this dotted line. That slope of 0 becomes the derivative graph's x-intercept. What was the graph doing to the left of this? It was increasing. So I'm going to draw up here. What was the graph doing to the right? It was decreasing. So I'm going to draw down here. So without too much hesitation, I mean, you could get into the particulars of what do I estimate the slope being exactly right here, and then graph exactly, let's say at a point like this, that particular y value. But I mean, the idea would be, it looks like that will be the derivative graph of that one. So there's 6 here for you to try. So go ahead, try those. Not too much practice in your textbook, but that would be about the end of what we want to cover in this curve sketching unit. So always remember, calculus is so much fun.